Hello and welcome to this video where I would like to go through some examples involving combined loading of shallow surface foundations. What I'm going to do is I am going to consider a rectangular foundation 2 by 4 meters on top of a soil. So let's draw the soil domain first, and I am going to make that 20 by 20. So like that, and then something like, we could make it 8 high. So that's my soil domain, and I might use a let's say a Tresca material for that. With the default parameters at SU of 100 and a gamma of 18. In the previous video I showed how to introduce a variation of SU, basically an increase of strength with depth. I am not going to do that here. I'm just going to stick with the default parameters. And then I would like to place a foundation 4 by 2 meters on top of this soil surface, and I would like to subject this foundation to a general combination of vertical, horizontal and moment loading. And question is how to do that. And so let me just first, before I do anything, draw the area in which the foundation draw the foundation. So let me just switch to XY view. So now I'm viewing it from the top, the soil surface from the top, and I want a foundation 2 by 4 meters. And let's make it 4 meters in the X direction and then 2 meters in the Y direction. So the bottom right coordinate is going to be 2. It's going to be somewhere down here, 2 comma minus 1. And then the top left corner is at minus 2 comma 1. So like this. So this is 4 meters. You can always click the lines to check the dimensions, and this is 2 meters. And I could then use a rigid block to model the foundation, except that it's a bit of a problem applying moment loading to a solid. So what I'm instead going to do is I'm going to actually use a shell to model the foundation. So select the area there and then press shell, and we have various options when it comes to shells. The basic option is a rigid shell, but you can have a rigid plastic shell, and then there's various sort of yield conditions. Mises for steel, of course, and there is Johansen and Nielsen if you want to do concrete shells or concrete plates. But the rigid shell will serve the purpose for this example here. And I'm going to subdivide that. So I want to apply moment about the y-axis basically. So have the moment in the most optimal way in relation to the dimensions of the foundation. So I'm going to subdivide the foundation before I do anything else with a line from here to here. So with a line from 0, 1 down to 0, minus 1. So I have now 2 parts of the foundation, and applying load could be done. I could draw a line here as well and then apply a point load at the center. Or what I'm going to do here is I'm simply going to use a line load to represent the say a vertical load could also be a horizontal load, but let's just say a vertical load like that. So obviously this is 2 meters. This is a line load, distributed load, kilonewton per meter. This is 2 meters. So whatever result I get out, I should multiply by 2, or I could also make the intensity of this reference load, this multiplier load, 0.5, so that the resultant force would be the 0.5 times the 2 meters, that is to say 1. And let's put standard fixities on that. Now, so that's vertical loading. So it can be done with a rigid foundation as well, and it's not too complicated to do. And of course, we could have a say a component in the y direction as well if we wanted, or something like that. So an inclined load, but let's just stick with a purely vertical load. And then, so that's one case we could consider, and then we could also consider the case where we have pure moment loading. So the moment, again, if you press the line, basically where load has been applied, there's 4 components to a load: x, y, and z forces, and then a moment about this local, the axis here defined by the line. And again, this is a moment in kilonewton meter per meter, so it's a distributed moment, so you wanna as well multiply that by 2 once the results are in, or alternatively just set it to consider to 0.5, because 0.5 times 2 is of course equal to 1. So you see these moment arrows here, and it's a bit difficult to see which direction it actually turns in, but if you pick the solid and then you can either make this transparent or hide it, or so you see the moment is about this axis in this direction, basically corresponding to the right hand rule in this case. So the local coordinate system, you can see that as well, is here. So minus 0.5 corresponds to a moment in this direction using the right hand rule. Okay, so that's pure vertical and pure moment, and then we could of course have a combination of the two. We could have something like, well, why don't we say minus 0.5 and minus 0.5, so like that. And then we are left to do the analysis, and let's see how that goes. And I'm again using the mixed element here, and just 1,000 elements, just for demonstration purposes, and with mesh adaptivity as usual. And we can call this V, call this M, and call this Vm. Okay, and let's see how it goes. So that is how it went. So a vertical load of 4,838, so 4.8 meganewtons. A moment capacity of 3.7 meganewton meters, and a combined capacity of well, moment equal to vertical equal to 2.87 meganewton or meganewton meters respectively for the vertical load, vertical force, and the moment respectively. And let's see the results. You can see the mesh has been adapted, and So this is the purely vertical load. You can see the failure mechanism is not completely vertical. There is a bit of, it's a bit unsymmetric, basically due to the fact that the mesh has been, the adapted mesh that's been generated, it has become slightly unsymmetric, and so there is a tendency for the footing basically to turn over, even though it is subjected to purely vertical loading. This is actually exactly what you see if you do full-scale tests of this type here as well. The moment it looks as expected, right? I mean, basically the foundation rotates. Try some shear dissipation. So that is quite expected, and the VH as well. Oh, the VM, sorry, will have a rotation as well. So yeah, less of a rotation than pure moment possibly, but it definitely rotates quite considerably. So that's basically how to do combined loading of shallow foundations.